are the characteristics of that line? Y equals kx. It's in slope-intercept form. What's the slope? Somebody be brave. Say it again, Caleb. Yeah, it's k. Good. Yeah, it's k. And what's the y-intercept? Yeah. So if we have a proportionality is always equivalent to a line with a y-intercept of 0, a line through the origin. And the slope of the line is just the constant of proportionality. Okay. So then we got to say two things here. We've got to say the intensity is proportional to the strength. Okay, well, how could we do that? Well, one thing we could say is we could say something like the intensity. So let's call this I. And this is going to be the weak. I set this up between classes. So this will be the weaker source, and this is the stronger source, light source, right? The weaker one's a little smaller, the stronger one's a little bigger, we'll say. So the weaker source here then, if I want to say that it's proportional to the strength of the light, saying that's one way I could say that is just equal to K, right? And let's let K equal, or maybe I'll call it something different. I'm going to call it C. Just some constant. We don't know what it is, right? That stands for the strength of the weak light source. How do I say that it's proportional to, inversely proportional to the square of the distance? What does inversely proportional mean? If I wanted to say that y is inversely proportional to x, how would I say that? Y is proportional to what? What does inversely proportional mean? If y is inversely proportional to x, y is proportional to what? One over x is correct. Yeah, there you go, 1 over x. So what's that mean then? As x gets big, y gets small, and vice versa, right? They're going to have opposite behaviors. And if I want to write that as an equation, wouldn't I just write that as y equals k over x? So if I want to say this red part up here, that's like saying that the weaker source is equal to k divided by what? It's proportional to the square of the distance, right? So I'm going to call this constant, instead of calling it k, I'm going to call it something different. That's probably overkill. I probably don't need to do this part, but I'm going to call it, I don't know, we're going to call it j over the distance squared, right? Well, the distance is x. Does that make sense? How could I combine both of those into a single equation at the same time? Well, I know if it's equal to some constant and it's equal to some constant of proportionality divided by x squared, couldn't I just say that the weaker intensity is just equal to some combined constant, k over x squared? Everybody agree? Did I need to break that into two parts? Not really. That's fine, Johan. Okay, is everybody okay with that? Let's see if it's proportional, directly proportional to the strength and inversely proportional to the square of the distance. Well, the only place the distance x shows up is in the bottom of the fraction. Otherwise, we're just saying k is some constant that's related to the strength of that weak light source. Okay, everybody give me a 1 to 5 on that. The blue sentence and the red sentence. Okay. Okay, so, right, so once again, we're just, if probably the x squared you're probably okay with. I'm guessing that the part you're confused about maybe is that k, is that right? True or false? Is that true? If I know it's inversely proportional to the square of the distance, I have to have an x squared on the bottom. The bigger the distance, if I double the distance, I'm decreasing the intensity by a factor of 4. Okay. What about that k? Well, the k is just there because that's going to represent the strength of the light source. This will make it easier. What is my intensity going to be for the stronger light source then? Oops. Well, I know that it's inversely proportional to the distance from the stronger light source, right? If we're saying that the distance is x from the point where we're measuring intensity to the weak source, then what's the distance from our measurement point to the strong source? Total distance is 12. Okay, good. So it's 12 minus x. So on the bottom, I've got a 12 minus x squared. That's my distance squared. So if I'm saying that the constant here on the top is k for the weak source, and the strong source is 5 times stronger, what value should I have on the top in the numerator of that fraction? What do you think? 5k, there you go. Good, it'd have to be a 5k because it's whatever, when the distance is 1, right? If x is 1 or 12 minus x, if the distance of either one of these sources from the measurement point is 1, if the strong source is 5 times as strong as the weak source, we should expect that it's going to have a 5 times bigger numerator, right? So it's got to be 5k. Everybody agree? Okay, if you take these things together, I almost feel like it's easier to see how we get those. Okay, so then what's my overall, I'm looking at the combined intensity of the two, right, at my measurement point. So what's my objective function going to be then? What's my objective function going to be? How am I going to build it? Yeah, just add them together. Just the sum of the two intensities, right? So the objective function, then it's going to be intensity is equal to k over x squared plus 5k over 12 minus x squared. And I can make that I of x now, right? Because the only variable is x. Everybody see that k is not a variable? Right? The intensities, whatever they are, they're fixed. We're not varying those. We don't know what they are, but we just know one of them is 5 times the strong one is 5 times that of the weak one. We don't know, but it's not a variable. It's not going to vary throughout the course of the problem. We can't vary that, but we can vary where we're choosing to make our measurement. So we're varying x. All right, so what's our domain for this function going to be then? Look at the picture. Look what x is. What's my domain going to be for x? Now look carefully. Okay, Caleb got a start on this. Gave us a good start, but we need to narrow that down just a little bit. Okay, could we, so Caleb's suggesting all values between 0 and 12. That works. Could we choose other values? Could we choose a value like 100 or something? I mean, we could, but can we reason that that's not gonna be good? I mean, that we know that the maximum. Oh, actually, we want to. No, we can't even, because if we read the problem, we can even make this simpler. Let's just read the problem. Problem says on the line segment joining the sources is the intensity the weakest. So it's got to be between 0 and 12. How come it can't be 0 or 12? Somebody? Say it again, Andrew. Okay, that's a good physical explanation. Mathematically, why can't x be 0 or 12? Okay, good, because we get an undefined intensity there. And I think you probably saw that, Andrew. You were taking that concept and telling us why it is physically. But look on the bottom of our function. If x is 0, this term is going to explode. If x is 12, I get a 0 on the bottom of this term. So the intensity function is undefined for both of those. So our domain is just 0 to 12. Okay, so now we can do calculus. If we just differentiate this thing, what are we going to get? So what am I going to get from that first term? See if you can do this without having to rewrite it. We want to make that into a power function, right? We don't want to use quotient rule. Agreed? Because I've got a constant on the top. There's no reason to use quotient rule. How should I think of that first term to take the derivative most easily? K over x squared, I should think of it in what form to differentiate it? I don't want to use quotient rule because I know the derivative of k is going to be 0. So why go through the whole hassle of doing quotient rule, right? It'd work.
K times 1 over x squared.
I could, but then that still looks like a quotient. I'd rather just use the generalized power rule. That's the easiest one we have, right? How could I write that as a constant times the power? X to what power? Yeah, I can just write it as kx to the minus 2 plus 5k times the quantity 12 minus x squared to the negative 2. Yeah, look at that. Now I can just use chain rule with the generalized power rule. That's a lot easier than having to do quotient rule, right? Okay. So what's that going to give me then when I differentiate the first term? What's that giving me? We got to make this quicker. Kyle, what's that going to give me? If I differentiate that guy. Okay, good. So I'm going to get negative 2k x to the minus 3, which I'll just write as an x cubed on the bottom, right? How about over here? So I'm going to get plus, or minus actually. I'm going to get plus 5k times negative 2, so that's minus 10k times the quantity, times hand, right, to the negative 3. That's supposed to be a k. So it's over 12 minus x squared cubed, right? Because the derivative of hand to the negative 2 is negative 2 hand to the negative 3 times the derivative of hand is going to give us a negative 2x, right? So I could rewrite that whole thing then as, I'll put the positive term first, how about? So this is going to become a positive term. I'm going to get 20kx over 12 minus x squared cubed minus 2k over x cubed equals 0. Okay, are we going to want to take a second derivative here, do you think?
Wait, Mr. Oya?
Yeah.
Under the 20kx, isn't it just 12 minus x third?
12 minus, say it again.
12 minus x third because there's an
Oh
x
yeah, how'd I
squared.
get a squared there? Yeah, you're right, it shouldn't be squared. How'd I get a squared there? Oh, I don't know how I did. I wrote it in here, but it shouldn't be. Okay, so then, yeah, that's going to change my derivative a little bit, isn't it? So that's going to give me 12 minus x, and then what's the derivative of hand? The derivative of 12 minus x is just a -1, right? So then that's going to give me a 10k over 12 minus x cubed, that makes that positive, right? Minus 2k over x cubed. And I want to find the zeros of that. Obviously, that's undefined at 12 and 0, which are not in my domain. Where is that equal to 0? Well, I could just add this term to the other side, couldn't I? I don't want to do that because I want to be able to plug stuff into this expression. So I prime equals 0 when this term equals that term, right? 10k over 12 minus x cubed equals 2k over x cubed. Well, what do you notice happens here? What happens to the k's? What happens to the k's here? They cancel. Okay, why are the math gods telling us that? What's that mean, that the k's cancel? Okay, yeah, it doesn't matter what the strengths of the two light sources are, right? One of them could be 100 watts and the other one's 500 watts, or one could be 1 watt and the other one's 5 watts. It doesn't matter, right? The point, as long as one is 5 times as strong as the other, the value of x should not depend on k, right? It shouldn't make any difference as long as they're different by a factor of 5. So the math gods are, once again, they're so wise. They told us that. Okay, now if I cross multiply, look what happens here. I end up getting 10x cubed equals 2 times the quantity 12 minus x cubed. Okay, so I could divide each side by 2 and make that a 5. And now, how am I going to solve this equation? This is kind of a nasty one, right? I'd have to expand this out. Whoops. And so I'm going to get, if I expand this out, I'm going to get 5x cubed equals 12 minus x quantity cubed is going to be, oh boy, what's that going to be? 144. Oh my goodness. I'm going to get 1440 plus 288. So what's that giving me? Is that right? Somebody cube 12, is that right? I'll fix it if I need to. Somebody check that for me. 12 cubed.
Just 12 cubed is 1728.
1728. Okay, I don't know how I got that. Yikes. 1728. Oh, how did I get 10? Oh, that was way off, huh? 1728. Oh, I know what I did. Minus, I should get 432 x plus 36x squared minus x cubed. I think that's right. 36 times 360. Yeah, that's right. Yeah, that's right. Okay. So then I would have to put this in standard form. I just expanded this thing out on the right side. So if I push everything to the other side, I'm going to get 6x cubed minus 36x squared plus 432x minus 1728 equals 0. So I got to find the zeros of that polynomial. Okay. Is grouping going to work here? 6? No, it's not. So we're not even going to mess with this. We're just going to graph that thing and find the solutions. And there's going to be a little shortcut I'll show you anyway. We're going to cheat a little bit here. We're just in this interest of making this a little faster. Okay, so if we want to find the zeros, okay, what do we find? If we zoom out on this thing, watch what we find here. And you guys tell me if there's a way we could have maybe done this a little bit more easily. Okay. What do you notice on this thing? How many times does it cross the x-axis? That's just an x-intercept. I mean a y-intercept. That's the only zero. Okay? It's not, we aren't going to have any other zeros, right? Because it can't turn again. It's a cubic function. And so it's got to have opposite end behaviors, right? Everybody see that? So this thing can't turn again. Okay, it had an inflection point. That doesn't make it look any better. So we got our one answer at 4.428 roughly, approximately, is where it turned. That's our only critical number. That fits. And did we even need to check all those? Really, we only needed to check the ones between 0 and 12, right? So we could have even just gone to Desmos and just set this thing up so it went from, well, I'm just going to go like from -2 to 14. And I guess I made that way too big, but you get the idea. That's a better scale, maybe. I'm just wasting time. I don't need to make this that big a deal. Something like that. Okay. So we can see that it only crosses once in our domain. So there it is. How could we have gotten that answer maybe a little more quickly? None of this is calculus stuff, but it's pretty good algebra stuff. Come on. There we go. How could we have gotten that a little bit quicker when we solved this equation? Right here we have the equation 5x cubed equals the quantity 12 minus x cubed. What could I have done to both sides there to make this a little bit easier? Anybody see anything? Oh. I don't know how I make it do that. It's pretty cool, but I don't know how to repeat it.
Could you have taken the cube roots?
Yeah. Look, I have a 5x cubed equals the quantity 12 minus x cubed. If I'm just looking for, you might remember this from Algebra 2, but you might not also. If we're just looking for real solutions, which is all we care about, for odd roots, you can take the odd root of both sides and you don't have a plus or minus in there. There could be some additional imaginary, there are some additional complex zeros with imaginary parts, but I can cube root both sides if I just want to find the real solutions. Okay, so what do we get? If I cube root both sides, I'm going to get the cube root of 5x equals 12 minus x, right? Well, if I solve this thing for x, I'm going to add this x term to the other side, so I'm going to get x times the cube root of 5 plus 1 equals 12. And what do you suppose 12 divided by the cube root of 5 plus 1 is? I'm betting that it's about 4.428. Okay? That makes sense? Which makes sense, doesn't it? Assuming I didn't make some dumb math error there. That's work? 2 point. Yeah, it works about right, doesn't it? Does it? 3. I'm wondering if I screwed something up right there, because I get slightly different answers. That's going to give me a slightly different answer than 4.428. Guaranteed. Oh, no, it's not. It's right. Never mind. It's right. Yeah, that's right. Cube root of 5 is going to be 1 point something, right? 1 point, what's that going to be, like 1.7-ish, something like that. So that's going to work out fine. Yeah, it works. Okay, that was just a little shortcut. But then when we make our table, I'm just kind of flailing around here like a turtle on my back. Okay, here we go. So we make our table then. We're going from 0 to 12. we didn't really want to take that second derivative because it was too much of a hassle. So we got our critical number was about 4.428. That's where we had a 0 of our first derivative. So we'll just revert back to the first derivative test. Let's just pick some test points. Like let's pick a test point at 1, and how about a test point at 10? And we'll just evaluate our derivative at those places. So if we go down here to our derivative function right here, and I evaluate this at 1, what am I going to get? If I evaluate this at 1, I'm getting negative 2k plus 10k over 11. So negative 2k plus 10/11ths k, that's, hang on, negative 2k plus, oh, that's 11 cubed though, isn't it? So I'm getting negative 2k over, and then this is going to give me, if I plug in 1, I'm going to get 11 cubed, which is huge. I'm going to get plus this really small fraction times k. So I'm getting negative. Okay? So at 1, it's negative. At 10, what are we going to get at 10? If I plug 10 into my derivative function, I'm getting negative 2k over 10 cubes is 1,000. So I'm getting a really tiny decimal times k. Minus a negative is plus. 10k over 12 minus 10 is 2 cubed is only 8. 10 over 8, that's bigger than, so I'm going to get a big positive term and a very tiny negative term. Gives me positive. So what's that telling me about the nature of this? And if this is my first derivative test, I've got a horizontal tangent. I'm going from a negative first derivative to a positive first derivative. So what is that? What is that then by the first derivative test? Yeah, it's got to be a minimum, doesn't it? We go from decreasing to increasing. So it's got to look like that. So we found our minimum for intensity. Okay, that's a pretty tough problem, I think. Pretty tough problem. I mean, there's a lot going on there, but I want several things I really wanted you guys to see. Okay, that's probably enough math. I didn't think that went very well, but hopefully you made sense of that. Give me a 1 to 5 on that. Do you feel like, how did you follow the logic on that? Okay, not bad, not bad. That's a pretty, like I say, a pretty tough problem. All right, go enjoy the sunshine a little bit. Get away from your computer. I will see you in a couple days.